Okay, a very welcome to all of you. And today we have to go on with time-dependent perturbation theory. We will actually subject ourselves to the mathematical treatment of this time-dependent perturbation theory. But before I start the mathematical argument, I remember there happened to have a man. He was a scientist, and he was performing an experiment in his laboratory. And this man was repeatedly working on discharge tubes. And the intention was that you could develop the rays within those tubes where he had to attain some state of vacuum. And this man repeatedly performed his experiment, and every moment he performed the experiment on these vacuum tubes, he failed to obtain a conclusive result. And one day he was fed up. Thought, come on, it's not happening. I'm not able to get anything out of it. So he takes a holiday. He doesn't attend laboratory for quite a long time. And then one fine morning he returns back to his laboratory. And when he returns back to his laboratory, he finds a piece of paper in his laboratory. And when he looks at that piece of paper, he finds a glow on it. And a question arises in his mind that he did not attend this laboratory for quite a long time. Why there is a glow on this piece of paper? And the man had discovered X-rays. The name of this fellow was Röntgen. In Russia, he is called Rankin. And you can understand the importance of X-rays in the modern time. It's a blueprint that gives the design of your bonal skeleton. So this is how science goes. Science does not mean that you will do it and it will happen. Most of the science has come via the failures. So let's proceed. We have already gone through the theoretical understanding of time-dependent perturbation theory. Now we will go with the pure mathematical approach for this theory. So what we have a perturbed Hamiltonian, and the perturbation is time-dependent. I have exclusively discussed the time dependence of perturbation in my previous lecture, right? So today we will go with the model, and the target is perturbation, and it is time dependent perturbation. So obviously you have a perturbed Hamiltonian, right? And if I say I have a perturbed Hamiltonian, that is H, that must be something H naught plus lambda HP. Right? As I told you yesterday, that to understand the behavior of your system, what you do is you send a pulse of disturbance, the magnitude of that disturbance is extremely small. But that disturbance gives us a lot of information about the system. So, the basic equation that we have in quantum mechanics that we use to solve for our systems is Schrödinger's equation. Now, I would like to write down the Schrödinger's equation. Okay, so what's Schrödinger's equation? It's IH bar dou by dou t. If I choose, say, psi n of t, and I will put this eigenstate in Dirac notation. This is your left-hand side of the Schrödinger's equation, and the right-hand side is simply your Hamiltonian operator acting on the eigenstate psi n, which is a function of time. Now this is my time-dependent Schrödinger's wave equation, and we understand that we can write down the current eigenstate in terms of the superposition of the eigenstates of the known eigenvector. So for that, I would like to write down this eigenstate psi n of t. What will be that? Yeah, this psi n of t, it will be a superposition, say sigma. Okay, I will use, say, a it's a coefficient dependent on time. Let me put some subscript here, a n of t. I will use an exponential e to the power of minus I e n of t by h cross, and an eigenstate, say phi n of t. Now what am I doing is writing down this eigenstate in terms of two time dependent parameters. This coefficient is dependent on time, and this exponential is also dependent on time, but I am incorporating a eigenstate which is independent of time. That is phi n. I should not write t here. So let me write, say, phi n of r. This eigenstate does not depend on time. Okay? Now, what should I do? Because the demand of the Schrödinger's equation is I want the eigenstate, the time derivative of eigenstate. So for that, I would like to differentiate this, isn't it? Because if I want to use this format of eigenstate in the Schrödinger's equation, I need the derivative of this eigenstate. So what will I do? I will differentiate this equation with respect to time. So if I do that, what I'll get dou by dou t of psi n of t. Fine? Okay? So here you can see this part will not take role in differentiation because it's not dependent on time. So you will have the two parts. One is this coefficient part. It's dependent on time. And another is this exponential part. It's also dependent on time. So I'll be using my uv in this case. What I'll have sigma. Okay? A dot n of t. Okay? The exponential will remain as it's e to the power of minus iota e n of t by h cross. Okay? It will have its own time independent eigenstate, phi n of r. Right? This will be your first term. Now the second term will be what? Plus sigma. Now a n of t will be as is. Now you have to differentiate this exponential, and you can see the internal derivative is minus I by h cross En. Am I right? This will be the internal derivative of the exponential, and your exponential will remain same, e to the power of minus iota En of t by h cross. And then you will have phi n of r. It's ket. Right? Okay. Now, what am I supposed to do? Is I'm supposed to use this eigenstate in my Schrodinger's equation, and I would like to replace the time-dependent derivative of the eigenstate psi of t in the left-hand side of Schrodinger's equation. Right? So I can do that. Now you see, what is in the left-hand side? You have IH cross. Then you have the time derivative of eigenstate. So what will remain inside? Yeah? Inside you are left with sigma A dot n of t, and then you have e to the power of minus iota En of t by h cross, and this is got its eigenstate which is independent of time, that is phi n of r. It's ket. Okay, this is it. This is the term 1. The term 2 is what? It is minus I by h cross En. Then you have, okay, you have a sigma, and then An of t, then you have e to the power of minus I En of t by h bar. Then you have phi n of r. It's ket. Right? This is our left-hand side of the equation. And what about the right-hand side of the equation? The right-hand side of the equation is h. But h is what? H is h naught plus, I will not use lambda right now, I will use it later on. So I will keep it as h naught plus hp. But this thing is multiplied by the eigenstate. What is that? That is sigma A n of t, then e to the power of minus iota En of t by h cross phi n of r. Am I right? Fine? Very right. Okay. So you will have two independent terms in the right hand side. The one term will be sigma An of t and e to the power of minus iota En of t by h cross. Then you will have your h naught phi n of r. This will be the first term. Okay? What will be the next term? It will be in terms of HP. So I will write that, but before moving on, you see this IH cross will multiply to this, it will remain as is. But when it will multiply with this, what you will get? Iota star will give you minus 1. It has its own minus, so it will become plus. So what should I do? I should put here a plus sign, because h cross will be gone. And I will remove the bracket here, because this IH cross is the part of this part of the equation. And for this, you have plus En. Is this clear? Clear? Yes. Can I move on? Okay. Now, you will have another term. What will be that? That will be sigma a n of t, yeah, e to the power of minus iota e n of t by h cross. Then you will have hp, and then you have phi n of r. Are you understanding what am I doing? Okay?
Plus.
Yeah, this is plus. Right? Come on, come on. Now look at this part. Look at this part of the equation. You have h naught phi n of r. What will it give us? En. What will it give us En? It will give us En. So this term and this term are same. This term and this term, they are same. Here you have to use the eigenvalue equation. That will lead us to the same energy eigenvector, because your Hamiltonian is a Hermitian operator here. Okay? So what you are going to get, this term will cancel with this term. Right? So what we are left with? We are left with this term and the term on the last. So what is the first term? Come on, tell me. So it is I H cross summation an dot. You keep in mind that this an dot is basically d by dt of an. So the dot is representing here the time derivative of your coefficient an. So what will be left here with? Okay, this is, yeah, come on, e to the power of minus I e n d by h cross phi n of r. Now this thing is equal to this thing. Is this clear?
Yes.
Clear?
Yes.
Now this thing is equal to this thing. Now what should I do? I will use the same basis and I will take a bra phi m of r. And what I will do? I will multiply this equation from left using phi m of r. Clear? Clear? So I can do that. When I do that, so what am I doing? I use an eigenvector belonging to the same basis with different indices, phi m. And I multiply this with the equation that is in front of you. Okay? So what will I get? Should I arrange it here? No, I will write it again. Come on. Tell me the term now. Come on. You have sigma. Yeah. You have a n dot of t. Then you have something e to the power of minus iota e n t by h cross. And then you have a cat of phi m of r and the bra of phi n of r. Is this clear? And what about the next term? That is sigma an of t. Then you have e to the power of minus iota e n of t. Okay, that's fine. Then you will have the matrix element phi m of r, the perturbation that you have introduced, and phi n of r. Is this clear?
This H cross E.
Yeah. Where is h cross? Here. Divide by h cross. Okay, what about this term? This term will exist for m is equal to n, because this phi m of r and phi n of r is a canonical delta. It is mn, and it will exist for m equal to n. It will give you 1. m equal to n. Okay? What? M equal to N. So with that, when I use this orthogonality condition in my equation, what I will do is I will trick my equation because I want to make my equation comfortable. So to do that, since I am using M equal to N, in the left hand side for N I will use M.
Yes.
And in the right hand side I have N. Getting my point? Okay, so what I will write now? Come on, come on. So what will I write now? I will write sigma A N dot of T e to the power of minus iota em of T by H cross. Getting? This is equal to, yeah? This is equal to sigma, what about the IH cross? That is here, I think, huh? IH cross. Or it is in the left hand side. It is in the left hand side. Sorry, it has to be in the left hand side. Okay, so this is IH cross is here, okay? So this is equal to, yeah, come on, tell me, this is AN of T, and then you have e to the power of minus iota En of T by H cross. And then you have the matrix element. Phi M of R, and then the perturbation phi N of R. Is this clear up to this point?
Yes, sir. Yes.
Are you following me?
Yes.
Okay, are you getting it? Okay. Now what can I do? I would like to bring this down, okay? What else? I would like to keep it in the left hand side sigma An dot of T. Okay? In the right hand side what I will get? 1 by IH cross. This is the first thing. Now the next thing will be what? Sigma, yeah? An of T. Very fine. Then I will write my matrix element. H M N. I'm writing it in the short form, okay? And e to the power of minus e to the power of iota En minus Em times T by H bar. You can do it and you will see it, okay? Because when this will come down, then you raise it up, then you will have e to the power of iota En minus Em times T by H cross. Clear up to this point? Okay? Now, let's write down this equation again. Now this is En minus Em by H cross. What is it? Yeah. En minus Em by H cross. What is it? Can you tell me? The only question I'm asking you. Give me the answer to this question. Come on. So what we have sigma An dot of T, okay, is equal to 1 by IH cross. Then you have sigma An of T. Then you have matrix element. You remember that this perturbation part has lambda with it? Okay? I would like to introduce that lambda here. So this is lambda, and then H M N, it's that matrix, okay? And then e to the power of I. Come on, you're not telling me. It's a Bohr's postulate. It's a Bohr's postulate. The conventional Bohr's postulate. What it tells us. Don't you remember that postulate? It tells us that the difference in the energy levels is what? You don't remember the Bohr's postulate? EI minus EF is H nu. Now you see, this is EI minus EF. Now H, I want to make it H cross. What should I do? I should multiply and divide by 2 pi. So this is H by 2 pi, and then you have 2 pi nil. Now this H by 2 pi is what? This is H cross. So EI minus EF divided by H cross is, what is this? 2 pi nil, what is it? 2 pi nil, come on. It's omega, it's angular frequency. This is omega. So here, it is e to the power of I omega mn t. Right? Okay? So for mn, this is I and f here, okay? You can choose it as m minus n. So this omega mn is what? It's the angular frequency. It's the angular frequency. Clear? You got it? So now what I have? I have an of t, an dot of t. I can write it as an0 of t plus an1 but with lambda of t plus lambda square an2 of t. It has to be dot, it has to be dot, it has to be dot, okay? I can expand it like this. Okay, I can expand this part also, which is an of t. What will be an? What will be the first term of an of t? Come on. What will be the first term of an of t? It will be lambda an0 of t, because you have lambda multiplied. So that what will be the next term? It will be lambda square an1 of t. Are you getting? Plus lambda cube an square of t plus so on and so forth. Is this clear? So you will have zero order calculation of perturbation, because you will compare the coefficients. Okay? What will be the zero order calculation? So for zero order, this term, which has a power 0, it has a dot on it, it will be equal to what? It will be equal to what? It will be equal to 0. Why? Because there is not any term in the right hand side without lambda. Right? So the first term will be what? The first term, that's called zero calculations of perturbation. That is, an dot of t will be equal to 0. What does that mean? That means an of t is constant. Am I right? Is it constant? Why? Because it is an dot. It is d by dt. And integration of 0 will give you a constant. Clear? Okay. Now, what about the second calculation? For second, you will have an, yeah? An dot 1. And what will come in the right hand side? An 0. Are you getting my point? And so on. So I can generalize this solution. I can write an, say, k plus 1 dot, okay, is equal to sigma. Now let me take off this sigma for the time being. Okay, what you are left here with? An of t.
K.
It will be only k. It's k plus 1. Right? And then h m n. Right? And then e to the power of e to the power of iota omega m n t. So you can calculate all the orders of the results of the perturbation. What is in the left hand side? It's a dot. It's a derivative. It's a... I forgot something. What was that? That was IH bar. IH bar is in the denominator of the right hand side. Okay? So now, finally I'm writing the amplitude. Now what is my amplitude? It is A. Yeah, it is A n of T is equal to 1 by IH cross integral 0 to infinity. You understand where from the integral has come? See, I have taken off the dot. Okay? So then you have here A n of T. But this one is K plus 1 and this one is K. Right? And the matrix element M H P N, right? E to the power of I omega M N T. So here we will stop. Okay? So this is the basic formalism that we have reached out. And what we have is the amplitude. Is the amplitude. Okay? And from the amplitude, you can calculate the probability density. All you have to do is to take the mode of scale of this amplitude. You will be calculating the probability density. And this probability density that you will be calculating, you will have the cases. You will have constant perturbation, constant time per perturbation, and you can have varying time perturbation. Okay? These cases we will discuss in our next lecture. So anybody having any questions? You got this?
Yes, sir.
So you can do it. So really, okay, thank you.